much, and I'd like to thank the organizers for inviting me here. You will see my topic is a little bit outside of maybe the main topic of the workshop. I joined this team from Tel Aviv, Niradin, Elsa Forhe, Elena Mohov several years ago, and they started to work on the so-called metric approximation theory for set-valued functions. And well, so now I'm doing it since a few years with them. Our aim is to mimic the classical approximation theory in our setup. And so now I will give you an introduction first, and well, I don't know what to say. So several people here, quite many people heard this or that of my talks, and this introduction is more or less always the same. So you will see familiar stuff, but well, I cannot not give an introduction. So first I'd like to explain you what we are doing, and then somewhere on the end some more recent results. Okay, so this was the wrong one. Okay, metric approximation set-valued functions. I start to explain what set-valued functions are. Then I tell a few words about metric approximation, and then to say what is different in this talk comparing to other talks, what are the types of approximation theory we're working with. So this time it will be integral approximation operators. Okay, set-valued functions. We are working with compact non-empty subsets of Rd. I will denote by K over D the collection of these sets, and we study functions, set-valued functions, which I will frequently abbreviate as SVFs. They also go under the name multifunction in some other areas. These are functions that are defined on a compact interval of real lines, and the values of them are compact non-empty subsets. So let me maybe quickly make a picture. What can we do? So we have an interval, and the value will be. So here I'm trying to make R2. So the value is something in R2, and here the value maybe is something like this. So it's compact. Okay. They have plenty of applications. Early applications, more theoretical, for example, in dynamic systems, control theory, game theory, differential inclusion, mathematical economics, optimization. Elsa, one of my authors, actually coming from optimization. And an example where you can imagine it makes sense to work with sets and not with particular points. Let's say you're in a board and you want to reach an island, yeah, on your weekend excursion, and then it doesn't matter which point exactly you reach. Yeah? You want to reach the set, but you don't care which point of the shore exactly you reach with your boat. In all these areas, what I told you, typically the sets people work with would be convex, and because of that, there is big theory of set-valued functions with values who are convex sets. Newer, with the development of computers everywhere in our life, geometric modeling came to the game, and here you can forget about convexity. So let's think about application, let's say in medical imaging. So there will be some medical images coming from CT, X-ray, whatever, and many objects are just not convex. Yeah? So some totally new approaches are needed, and well, as I told you, the entire theory is convex. Okay, so there is a list of some names who worked on it, and as you can see, approximation of functions with convex compact images is quite well developed. Let me tell you, for example, about this paper of Richard Whitley. You see how old it is. He actually made Bernstein operator, a natural adaptation in this situation. So let's say a set of cross sections of a function is given, and so here, and we want to find approximant. So he kind of mimicked within the theory of convex sets the Bernstein polynomial operator. It works perfectly for functions with convex images. He can prove it. However, this is also part of his paper. If the function doesn't have images who are convex sets, then this set of polynomial Bernstein operators still converges, but to the convex hull. Yes, so it fills the gaps. And this is a very, very typical situation. It's called convexification. So the limit of the approximant is a set-valued functions whose convex image with convex images, so typically would be convex hull of the image of what we want to approximate, and clearly it's totally useless if you want to really work with functions whose values are not convex. Okay, some other names, time's running, so I jump over it, you can see it. Pioneering work on, a pioneering work on approximation with general not convex images. Artstein, piecewise linear approximation would be suitable in this situation with methods which we later term metric pairs. So basically this is the situation. I have a point here. I want to connect it with a point here. Which point to pick here? So Einstein says pick metric pair. So what's a metric pair? This is my next slide. I take any norm in RD, and then for point B and for a set, for point A and for point C, this is a projection, and metric pairs of two sets or pairs of points AB. A is an A, B, and a B, such that A is a projection of B or B a projection of A. So here are some pictures. So all these connected points are always metric pairs. Here is a special metric pair which gives us the Hausdorff distance. So Hausdorff distance can be rewritten using metric pairs. Okay, and this is exactly the idea of Einstein, what I told you, that when I start with a point, look at the next set, what is the point to connect, just pick metric pairs. It can be one, it can be several, depending on the situation, just connect them. Okay, but I told you by integral operators. Yeah? So I'm going to work with integral operators, how to integrate set-valued functions. There are different approaches, and probably I would say from my point of view the most classical, most used approach is the so-called Ullmann integral. Here it is Ullmann integral. I will now explain what it is. For a set-valued function f, a single-valued function as such that s of x, so it's a point here, this is a set, s of x is an element of f of x for all x is called the selection, and the construction of Ullmann integral is the same. The following, I take all possible integral selections, integrate them, so I have every time a number, so I put these numbers in the set. This set is the integral of the function. It is well known that the Ullmann integral is always convex and compact, even if the values of f are not. So we have an absolutely classical case of convexification. An example, I showed it a few times, so some of you saw this example. I take a function f whose values are 0, 1. The set consists of 2 points 0, 1, a constant function. And then this is the average. And I want, of course, to make the things meaningful, that the average is this constant function, the set itself. No, that doesn't work. So this is the graph of the function, so the value at each point consists of 2.01. Let's see what the integral is. The integral is, as I claim you this. Why? Because I take number alpha, I take this red selection, right? Gives me exactly the value of alpha, and this is what I can do for any alpha from 0, 1. Yeah, so it's not an average. Yeah? It filled the gap. Fill the gap here. Yeah? So it really, the result is the convex hull, as you can see. Yeah? The convex hull of this set. So such methods are of course useless. They're useful, very good for convex setup, not for us. Okay, we took too many selections. Let's take less selections. Metric selections, not just all integral selections, metric selections. What's it? This was introduced by Nira, Elsa, and Alena a few years ago. Some intermediate step we take it. Oh, I see. I made a mistake that I by mistake removed the definition of this set. These are chains. Chains means that well, I have a partition, and here I take particular points, but all neighboring points are always metric pairs. So if I have several sets, I always go to a metric pair, and then we take such a chain, and we approximate it, for example, by a constant, piecewise constant function. This we call a metric function. Now, a selection as is called a metric selection if it's a pointwise limit of a sequence of chain functions when the size of the partition goes to 0. Well, it's not so important for you to look at it. The point is, these are some examples of metric selections. This is a graph of a function, so the value is always a subset of R, and these red lines always gives us metric selections. So because we only use metric pairs to define them, the metric selection is constant in every open interval where the graph stays in the graph of F. So basically these are lazy selections that don't change value if they're not forced to. So for example, this function went, and here it's a whole, it cannot continue with this value, then something happens. If it's not forced, then it always stays constant. And I will denote by this capital F of F, AB, the class of set-valued functions of bounded variation with closed graphs. This is set we work with. Collection of results. Through every point there is always a metric selection, so I can represent the entire graph as a collection of lines which are metric selections. It's a good set in terms of pointwise convergence. Pointwise limit of metric selections is a metric selection. And then finally, the most useful property is that we can control metric selections by the properties of the function. So for example, this inequality says that the total variation is bounded by the total variation of the function f. F was a bounded variation with respect to the Hausdorff metric. And let me explain you that we cannot expect it from any selection. Because if I have a graph, let's say something like this, graph of a function, it's a function of bounded variation in the Hausdorff metric, then if I consider just an arbitrary selection, I can have variation as large as I want, because I can take this selection like this. But in this case, it doesn't happen. And the same also, the metric selections inherit properties of continuity and smoothness also from the mother set-valued functions. So usually we use some local one-sided moduli of continuity, something like this. It's all inherited. Again, cannot be promised for arbitrary selection because this arbitrary selection can vary as it wants. Okay, this is the metric integral. Well, exactly the same idea. We take individual selections, integrate them, and the set of values gives me the metric integral. The only difference is here not all selections, but only metric selections. And then it works very well. Back to our example. This is exactly the situation. I have only two metric selections. So the average is in this case exactly the set itself. Okay, we realize that to work with this construction within approximation theory, we need to introduce a kernel. So the K here is real valued functions. Weight function, we call it weight function. So it's real valued function, so it can be all, this idea can be extended. And this is now what we do with it. So I introduce this kernel exactly because we want to study integral operators of this form. So now metric adaptation of integral approximation operators. Take an integral approximation operator, you know, from the usual real-valued approximation theory, and replace the integral, put here set-valued function, replace the integral by the metric integral. This is the idea. Okay, so this is sorry, too fast. This is here kernel, yes, so the kernel function of two variables xt. It's a given kernel with some properties. So of course we need to have this operator is an approximation operator in the original setting. Yes? So basically what we need, roughly speaking, is the localization on the diagonal. Well, I spent lots of time in my life working on some Bernstein type operators, and that's why it's my first example here, the Bernstein-Dürrmayer operator. Yes, it's a variant of the polynomial Bernstein operator for integrable functions. The original Bernstein operator works only for continuous functions, doesn't work for functions with discontinuities. Kantorovich operator is another guy of this family. And these are just examples, must not be like this. Okay, a remark at this point is that exactly at the time we were working busy with it, we learned that Michele Campiti, my dear colleague from Italy, studied adaptations of integral approximation operators based on the Aumann integral in the convex setting. So exactly the same two operators, for example, the Bernstein-Dürrmayer and the Kantorovich operator, he studied them in that parallel setup, convex setting, Aumann integral. It must not be that, yeah, it could be something else, and this was actually our first result. This is where we started with, when we started to work with integral operators, metric Fourier series. This was, for example, the talk I showed in Budapest a few months ago. Some of the people here were there. The partial sum of a Fourier series is an integral operator with the Dirichlet kernel. And this is how we arrived to studying integral operators. So our original aim was to develop somehow Fourier series for set-valued functions, and we realized that the way to do it is through metric integral with the Dirichlet kernel. And okay, there are some differences that in set-valued functions, even the periodic set-valued functions may have selections that are not periodic, but let's not focus on it. We were very excited about this week because we Googled for hours, but it seems like there are no works on set-valued Fourier series, not even in the convex setting. So it seems to us that we were really the first people to define Fourier series for set-valued functions. Okay, last minute. Convergence. Here Tn is my integral operator where the kernel is good, yeah? And then these are the results. F of bounded variation with closed graph. If F is continuous, then we have the convergence at point in the Hausdorff metric, and F is continuous in the closed interval, then the convergence is uniform. I work with functions of bounded variation, so the discontinuities can be only jumps, and this is the analog theorem for the jumps. Then originally we can describe the set where it converges to in terms of the metric selections, and of course we were not exactly happy about this because we want to have a result in terms of the function f, and unfortunately it's not possible. This is the set once again, this is my last slide. Unfortunately, it's not possible in the arbitrary setting, but under some meaningful assumptions, we can show that the set where all functions converge to is exactly this. is the metric linear combination. I didn't define it, but some meaningful linear combination of 1/2 of the left limit and 1/2 of the right limit. And this is exactly what we see in this situation for the original operators for the on the real line, yeah, for the real valued functions. It's not true in general case, but under some reasonable assumptions, this is true. Thank you for your attention.
Okay, thank you. Other questions?
Yes, please.
How your typical approximant looks like in Fourier case?
Oh, you mean just really to make a picture?
Yeah.
Well, you see, I know how to answer your question. We think of our function let's say this was my function. This is the same for all these integral operators. We think of our function as a collection of metric selections. So I don't think about this object in several dimensions. I think of it as a collection of whatever, yeah, of these individual functions and so on. And then I take the partial sum of the Fourier series for each individual functions and pack them together. And this is then the result. So this is the strategy. This is the logic that the graph is split into individual regular functions. They are approximated, and then it all put together.
It could be some problem about how this picture looks like. I mean, there are some maybe new questions after that. How they could look.
Well, I don't know, it converges in the points of continuity converges in the Hausdorff norm. But this is it. Think of individual functions, and then each of them gets its trigonometric polynomial, and then all these trigonometric polynomials are put together. So I don't know, yeah, I don't know what to say about that.
Okay, there's another question.
It's a follow-up question, because I guess there are several ways to represent your set-valued function as a collection of such.
Oh yeah, they are not disjoint. Yes, all of them. There are many of them. Yes. They are all of them.
And then if you go to the Fourier space,
Yes.
you have uniqueness of the representation. Do you have uniqueness of the representation in the Fourier space? Or do you have different... if you choose...
We tell all of them.
Yeah.
We take all of metric selection. We take all of metric selections, and then what comes out on this other side. But that's once again, yes. So this is not that I put here lines which are disjoint. But no. Like for example, here it could be. Let's say I could go here and then here is constant, yeah. But let's say, yeah, something. Well, it's not a metric selection, but whatever, yeah, they can intersect, all of them. So the result is one set, it's uniquely determined.
Maybe another very short question.
Go to have lunch, yeah, we all want to
Just
go
to
to have
refine
lunch.
this, so when you choose them, you take them with the equal weights, all the metric selections, or
No, well, yeah.
you know to take them with different weights.
But there are a continuum of them.
Yeah, but you have to put some measure behind these metric selections. Is that measure the back measure
No,
with
there
respect
is
to the
no.
choices or something else?
Perhaps I don't understand the question.
Okay, so maybe you just...
Yeah, maybe
later,
discuss it,
so,
thank you, yeah.
So, thank you again.
Thank you.